Thank you very much, Tom, for introducing us. I hope you can see the presentation all right now. Okay.
Yeah.
Thanks also a lot for Effie for giving us this opportunity to present estar at the webinar. So I'll directly start. Go for it. Stability is a key concept in ecology and evolution, and stability has fascinated ecologists as early as since the beginning of the 20th century. For example, starting with Charles Elton, Lotka, Volterra, and the seminal paper by Hollin in 1973. I myself really like this paper by Van Meerbeke that summarizes the history of development of stability research, and he basically distinguishes two schools of research. One school that studied the research very close to equilibrium. This school is shown in the cyan or light green on the top. So it started with the works by Lotka and Volterra and the researchers that studied the response to perturbations, resistance, resilience, and mathematical theory. And on the other hand, we have research initiated by the seminal paper by Hollin in 1973 that is happening around regime shifts, domains of interaction, and also that is heavily attracted to social ecological systems. This school of research recognizes the existence of several different stable states and doesn't limit itself to a single state. Importantly for this talk and for estar, we actually limit ourselves to stability concepts of the systems in the close vicinity of one stable equilibrium. So we basically are more in line with the school of thought, research school that is shown on the two top lines in green. And I will just pick here the pointer to not wave my hands because it doesn't help here. So as the interest in stability appeared among ecologists, it grew very quickly. And for example, already in 1997, Grimm and Wissel found 163 definitions of 70 different stability concepts in literature. And importantly, some of these different terms were used to mean the same thing, and vice versa. Very different terms were used to actually mean the same thing. So basically, the stability was surrounded by a lot of controversy, and the confusion was growing. And before we try to understand that controversy and reasons for the confusion, I would like to bring all of us on the same page with regard to several terms that we will be using throughout the webinar. So when we say system, we usually refer to a population, a community, or ecosystem. That's what our systems we are dealing with are here. State variable is a variable that is used to quantify stability properties of a system. And for example, if we talk of a population as a system, then the state variable that describes the population is abundance. If we talk of a community, then several different state variables are possible. For example, one state variable is species richness or total abundance, or one of the biodiversity indices with which one can summarize a community dynamics. We also talk about baseline and reference dynamics, and that is the dynamics of the undisturbed system. So while we want to measure the response of a disturbed system, very often it is necessary to have a reference or a baseline system, and it can be either a separate system that basically is as close as possible to our disturbed system, so that mimics it, or it can be the disturbed system itself prior to disturbance, so where it is supposed to be in a quasi-stationary state prior to being pushed away from that state. And then we also have to be clear about what we mean by disturbances in our presentation. So disturbance is a change in the biotic or abiotic environment that alters the structure and dynamics of a system. And Van Meerbeke distinguishes three types of disturbances: pulse, press, and ramp disturbances. Pulse disturbances are short-term and sharply delineated ones that increase in their intensity very quickly. P on this plot is intensity, and they also very quickly decline in their intensity. And T on the x-axis is time. Examples of these disturbances are droughts, cold spells, fire, and heat waves. Press disturbances are those that arise abruptly and then reach a constant level that is maintained. So for example, a ground level can be fluctuating around a certain level, and then around 70s here, it dropped to a new level, and then it's not super stable, but it fluctuates around this new lower level. Other examples of press disturbances are deforestation and habitat loss. And finally, REM disturbance is the one that is characterized by a long-term and gradual change of the environment, for example, climate change. So Ian Donoghue suggested that the controversy is because that controversy that surrounds the stability concepts in ecology is because stability is a multidimensional concept that tries to capture different aspects of the dynamics of the system and its response to perturbations. And they also suggested that different definitions of stability actually relate to different aspects of stability. So to try to demonstrate this a bit better, what we mean by multidimensional character of stability, I here show you 4 stability properties. I give their definitions and in a very simplified pictogram way, try to explain whether it's good or bad for the system. So what is a high or low stability? So persistence is existence of a system through time as an identifiable unit. And we can see here that the longer the system persists as a defined identifiable unit, the better it is for the system. Invariability is defined as the temporal constancy of a state variable following the disturbance, and it's often measured as the inverse of the coefficient of variation of our state variable. And in this exemplary case, our state variable is biomass. So we are talking about the system that is community, and we are measuring biomass here. And resistance is the amount of change in a state variable following a disturbance. So we can have here 2 different systems. One changes slightly after a disturbance is applied to it, and the other one changes a lot. And therefore, the resistance is high in this system and low in this. It can be a bit counterintuitive because in fact, the magnitude of change is much bigger in the systems with lower resistance. And something happened. Recovery is capacity of a system to return to its pre-disturbed state. And in literature, we find different aspects that can be measured for recovery, such as rate of recovery, recovery extent. Here we exemplify just rate of recovery. So it's the speed with which the system, after perturbation, returns to its quasi-stationary equilibrium, to its pre-disturbed state. So different stability metrics, I just exemplified 4 of them. Importantly, they do not necessarily correlate. And that's what we call dimensionality of stability. So in case all the stability properties correlated very highly with each other, as here on the left-hand side, we would use one metric, say resistance, and infer the other stability metrics. But in fact, for several different study systems, some studies are shown here on the top, on the bottom, it was shown that very often, at least several of the stability properties correlate only weakly with each other, which means we have high dimensionality of stability. And so we have to measure different multiple stability metrics. In addition to the need to quantify this variety of stability metrics, the previous research has also shown that different groups of researchers quantify different stability properties. Thus, empiricists usually quantify variability and resistance. So you can see here in blue and green are observational and experimental. Research focuses heavily on variability and resistance, whereas theoretical studies rather focus on measuring asymptotic stability properties and resilience. So there is a big divide between empiricists and theoreticians in which stability properties they measure. On top of these rather conceptual challenges surrounding ecological stability research, there existed a very practical problem. Until today, there was no single tool to quantify different stability metrics. And so in response to that, Ludmilla and I, with another group of colleagues, we joined the efforts and developed estar. And now I give over the floor to Ludmilla, who will pick up and present you what estar can do.
Thank you, Viktoriia. Yes, so let me get it. Yeah. So as Viktoriia said, we have this toolbox, and I'm going to present what is inside in sections, and you understand why. And actually, I can put it on the chat, the link to our paper, because can you maybe do it, Viktoriia? I don't have access to the chat right now. Because this is actually how we start our paper by saying, okay, we have two major groups of functions. And one of them is what we call the functional metrics. And these are, they depend on data that is organized as a time frame. So it can be, as you see, a variety of population sizes or trait values, and there are 6 of them that we use, and we are going to go through each one of them. But before we do this, I'm going to, as Viktoriia said, there were like over 100 definitions of stability. So this is because of how people assessed, right? In many cases, they were talking about the same concept, but they were assessing it differently. And one of the ways to separate it is by measuring it as based on what we call a functional metric, and this would be a single variable that you can measure over time. And this, as I said, could be population abundance or some relevant traits. For example, the levels of stress hormones in animals or an ecosystem function. Or you can assess it based on community abundances through community dissimilarity. And this, for our community metrics, we have an argument inside the functions. You'll see it all at work soon. But we have a time where this is already one of the ways to define, okay, which specific metric are you calculating? And this applies to all of them. On top of this separation, we can also have different ways of assessing how our variable of choice is changing. You can think that if you're studying a system, that if you're assessing the stability of a system, you can think that there was an original undisturbed state that might be more or less known to us, and a disturbed state that's where you see some change in the dynamics of the system. And we can measure this change in terms of the variable itself. So if you're thinking about a population abundance that decreases very strongly, this would be a straightforward way to measure it. But you might want to scale the response of your system. And one of the ways to do it is through the log response ratio, which is basically the log of your variable in the disturbed state over the baseline, so the undisturbed state. Or you can measure it as a difference, as an absolute difference, and then use this two responses to calculate the measure based on them. And this is also an argument in the function, again, a way of specifying exactly which metric you want to calculate. Finally, we have the very important question of the data. Okay, what kind of data do you have about your system? Because we know that time series data is not as ideal as you'd like. We don't have monitoring over long time monitoring and regular monitoring of many ecosystems before and after some kind of disturbance happened. And we try to take account for it by giving a variety of ways in which the user can enter the data. So a very common, not common actually, but a very nice way would be if you had either 1 or 2 time frames of your variable observed in the baseline system and observed in the disturbed system, equally measured. This is often the case for experimental settings, but maybe there are some natural places where this is available, and it can be in the same data frame or in separate ones. It's not a problem. But what might be even more often the case is that we have the single system for which we have some time of some time interval where it was monitored before a disturbance happened, and afterwards we kept monitoring it. So the time frame before the baseline amount of data is not as big as you would like to not to establish what would be the reference value for it, but you work with what you get, and we have arguments for this too. So the B argument defines whether your data comes from a real baseline, from an independent baseline, sorry, or if it comes from a disturbed system. And so you can calculate with whichever data you have. And besides deciding, okay, what type of data of baseline I'm working with, we also have variables to deal with the name of the variables inside those data frames. I'm presenting all this so we can concentrate on the varieties of metrics instead of, okay, how exactly do I get my data in? But it's basically this. You need the name of your data frame and then the name of the variables inside it. And so all of this was for the functional metrics, right? The ones that are dependent on a single time, on a time series of a single variable. For the compositional ones, where we are based on community data, we expect the user to have some community data for the baseline and some community data for the disturbed system. And community data is basically your time variable and the variable, the abundances of your species or functional groups. And because we calculate compositional dissimilarity as our measure for how this community is changing, we use the vegan, so the veg-dist function from the vegan package. So you can also, sorry, this parenthesis is wrong. It should be referring to method and binary. You can use those to choose exactly which type of dissimilarity you're calculating among those available in the vegan package. We're not going so much into detail here. But yeah, you have this flexibility. Yeah, so for our demo, we are going to use data from an experiment with the Chlorpyrifos insecticide. It was applied to a community of aquatic microinvertebrates. There were 128 species in the original data, but they were grouped in functional groups, and we are going to analyze them like this because it's easier to visualize and to think about what's happening. So here we have our time of observation. They were observed for 56 weeks after the application of the insecticide, marked here by this gray line. These are the log mean abundances. But as I said, most of our functional metrics we can calculate based on the log response ratio. And this is what they look like over time. Just for you to have an idea, as we go through the slides of how we calculate the metrics, this is what we'll be thinking in terms of. And just for those who are following in the, with the code, you will see that like a lot of what the code, especially the beginning here, a lot of it is just about me organizing this data in that structure of having our disturbed and undisturbed data together. Because in our experimental design for this community, we had 4 replicates for the control and 2 replicates for each. And the way that I calculated all the metrics was by combining 1 control with 1 disturbed. So in the end, we had 8 pairs of baseline and disturbed system to calculate a variable and extrapolate the value of stability. And you'll see that most of what I do here is a lot, the code sound looks very long, but as you see, the part of estar is small. The rest is mostly about combining my data in a format where I can do some factorization of the code. But don't be frightened by it, so to say. So I won't be going back to that code so much because the important bits I'll be showing here in this presentation. So as I said, the code is quite straightforward. Each metric has the name of the function, basically, sometimes abbreviated. And you go through some arguments, the arguments that are presented to define what is the exact metric you want. So we'll start with a invariability, right? We'll calculate the functional type. So based on a single value, here you can already see that we'll use the log response ratio of control and disturbance. We're using abundance, right, as our variable of interest, so to say. For invariability, there is an extra argument, and this is called the mode, because invariability can be measured either as the size, how big are the residuals of a linear model that we fit to our data. So we get our data points after disturbance happened until the end. You can actually choose the interval. And we fit a data model and we look at the time at the residuals of the model to see how their magnitude. Or, as Viktoriia said, we look at the coefficient of variation of that data. And in our case, we will use the coefficient of variation. And finally, as I said, you have to choose a time frame for which you want to calculate that invariability, right? Because you can think that it doesn't really make sense to include the beginning, the before disturbance, into my calculation. And the rest of the arguments here are just my data. This is code that is available with data from the package, but it's just for you to see that it's really like the names. And when we're talking about the compositional, so based on the similarity of the whole community over time, we used Bray-Curtis dissimilarity because we have abundances, and there is much less arguments. We have the type of metric we want. So this case is compositional, as I said. You define for which time frame it is relevant for your whole data set, right? And then you give the names of your community data, of the data frames contain your data, and that's it. And how to interpret our results? So invariability, the larger the magnitude, the higher the stability, because you can think that the more it's varying, the less the less variable it is, the less stable. And kind of contrary to what we like visual inspection might indicate us here, we see if we look at the groups by themselves, so at the functional metric, so to say, we see slightly higher stability actually for them. And this always gets me, Viktoriia and I, thinking, is this really correct? But if you look at, for example, the herbivores, you see they're the yellow line here. Now you see them quite a bit like varying as we want to check. Whereas here in this graph, it's slightly more stable. So we are assessing information that just just trusting our visual inspection, it's not, we might not get. And actually, if we look at the compositional invariability, we see slightly lower invariability in the under high concentrations of the insecticide. So I mean, this is for you to see how different aspects of instability, how they give you different information depending on how you calculate them and how estar can take account for it. So don't be so worried about this data. But we want you to think more about the metrics that we are assessing here. Then we have resistance, and resistance is, as Viktoriia said, is that how much your system responded to the disturbance, and this can either be measured at a defined time. So this time you need the rest time for it, where you say, okay, I want to measure resistance at a specific time that is relevant for me. And you'll see that a lot of the arguments in our functions, we ask the user to define, because if we try to create a function that would apply for all kinds of systems we have with all kinds of assumptions of of equilibrium, it would be very hard to have something that people could use. So we really need the user to know their system, or at least be willing to explore different ways of assessing what their system is doing. And this is the case for resistance. You can say, okay, I want to check what the resistance was in a specific time, or you can say, okay, I want to check the maximum change in my variable, in my response, in this case, so the log response ratio. I want to get the highest value, and this is the one I want to measure. It doesn't matter where it happens, I just want the maximal one, and this is what it's going to do. So you define the time frame for which it should be searched, and then it's going to be measured either as the log response ratio or as the difference, if that's the choice of the user. And the same for compositional, right? Apparently my slide disappeared, but you can imagine that instead of having the log response ratio, you would have a curve of the dissimilarity here, and it's the same. You can either choose a specific time to look for it or have the maximum. And we looked for the maximum value for our example. And resistance, as Viktoriia said, the maximum value of resistance is 0, because this would mean that your system didn't change from where it was just before disturbance, right? And if it's higher or smaller than 0, then it's either an undercompensation if it goes down, so to say, or it's an overcompensation if it goes up for some reason as a response to that stimulus. As we can see here, we have under low and higher concentrations of insecticide, the groups behave differently. You see that herbivores seem to have a slightly overcompensation, whereas in the higher concentrations they decrease just like the others. And this is a slightly different picture that we see once we calculate the compositional one. Once you take the whole community, you see that the value for high concentration is higher, indicating some kind of overcompensation of the whole community. Then we have the recovery rate, and the recovery rate we measure by feeding again a linear model to our data points and looking at the slope. So you can imagine the higher the slope, the faster the recovery is. There are no special arguments for recovery rate, so you just have to define, okay, is it functional based on a single variable, or is it compositional based on community data? And then your choice of response, in our case, we'll look at log response ratio and the time frame for which to look. Here I looked for the whole time since the disturbance. You could look from maybe here if that makes more sense for your system, or you can explore. And since it's a rate, right? So the higher the absolute value, the faster the response. And in our case, we see very low rates, because you can see that our system is not the most responsive ever, right? We see a drop here if we take into account the detritivores, but actually we take into account the whole time frame. So I'm thinking those points, they are leveling up, making our fitted model more straight here rather than a very nice inclined curve. But as I said, you can play around with this when you're measuring to see when it makes sense for your system. Finally, we have the recovery extent. So how much the time your system changed at a given time that you can decide. So you have to tell, okay, let me check how far I am from my original state at a given time. This is given by the T recovery argument. And it's going to measure again either as a mean of log response ratio between the disturbed and the baseline values of abundance in our case, or as a measure of dissimilarity. And again, its maximum value is at 0, because it means there is no difference between your previous state and your disturbed state. And higher and smaller values indicate under and overcompensation. And again, we see a bit of a variety of behaviors from our different groups, all of like many indicating negative, not many, right, but a couple of indications of negative, of undercompensation, so to say, if we look at them separately. But then when you look at them at the whole community, it seems like the whole community as a whole, the similarity of the community is overcompensating slightly. The fifth metric, if I'm counting right, is persistence. And as Viktoriia said, she presented it as the identification of her system as a whole unit, so to say, as a identifiable unit. And we did it by measuring it as the proportion of time that our variable state inside a given interval. If it's a functional, if you're measuring functional persistence, this interval is determined as the mean of your baseline plus and minus its standard deviation. And then we look for the whole time of response of your system, how much of this time did your variable stay inside that limit that you defined? There are no special arguments, so basically the type and then your input and the time frame that you want to evaluate. And the same for dissimilarity. You give a limit of upper and lower dissimilarity that you want to allow for your community to still be your community. These are defined by the users. It's not like here that is calculated by the functions. These are entries that the user must provide. And again, we calculate that proportion of time. Since it's a proportion, we stay between 1 and 0. And the higher the persistence, the more stable the system is, because you can think that it stayed longer inside that interval that we define as something that is acceptable for that community. And here again, we see a couple of different answers. So it's slightly higher when you look at the groups individually, slightly higher the persistence than when you look at the community, indicating that maybe the community changed a lot, even though the groups inside it stayed, I mean, not particularly well inside their limits. And a big change for herbivores, even though they seem to be more stable under higher concentrations of the insecticide. And finally, we have the overall ecological vulnerability. And this, true to its name, it's really an overall description of the behavior of a system, because we measure the area under the curve of our response variable. So in this case, we are still measuring log ratio, response ratio, and we calculate this area for the time frame of the response, and the same for the dissimilarity. So we have our data, we calculate that area. And this, because it calculates this area, it encompasses all the other metrics, because you can think that the rate of recovery, for example, is going to determine how high this curve will go, so to say. The recovery extent as well. If it goes higher, it's coming back to what it was. If it stays low, it's going to another system completely, so to say. If it varies a lot, so what is measured by variability, it's so the area is also going to change. So this is a nice encompassing metric to be explored, and we allow this with the package. And for us, we see that, first of all, since it's an area, it's always bigger or equals to 0. And the higher the value, the less stable the system is. It doesn't mean that the system is lost. It just means that it's unstable. So it might be just having like a zigzag of a curve, or it might have a big shootout or a big shoot down, and this affects the area. And again, we see herbivores seeming to be quite less stable under the higher concentrations, whereas in other metrics they had a different behavior, right? So as Viktoriia said, we seem to be looking at the stability at different perspectives here, depending on what we measure. And again, at a higher, when you look at the composition, we see a generally higher value for the overall ecological vulnerability. And here I'm like these values, sorry, I didn't say this before, but these are means that I did just for us to get an idea, as I said. So these are the 6 functional metrics and how you can use the arguments of the functions to specify which exact variant, we call them variant, of that metric you want when you're calculating your for your system. Then we have the second, so you think of a toolbox, sometimes they have the upper part and then you take it out. Now you have the Jacobian metrics. And these are the ones that were quite exciting for us to tackle because they are based on the Jacobian matrix, so the matrix of interaction strength between species in a community. And they're I wouldn't say they're exclusively, but they're largely used in theoretical models. And we wanted to find a way to make them accessible for empiricists to have data that could be somehow to which we could apply these functions. And there are 5 of them. I will again have this schematic presentation, but contrary to my previous schemas where this time series literally represents a variable that you have. Here, remember, we are talking about interaction strength. So it's not like we have a single variable that changes over time. We have the interaction strengths, but this was an easier way to represent them. And for data, we only need one data input, but it's going to be you're going to have to work for it. Because as I said, we need the interaction strength between your species to calculate these metrics. And this is given by, we give it the name B. You soon see why. And this is basically a matrix where each element measures the effect of the species in your columns on the species in your rows. And species or functional groups. In our case, we use functional groups, right? And this is data that is quite hard to be measured or even calculated. And in estar, what we do is that we can use the Mars package. Mars states for multi autoregressive space state models. And this data, they use this package, they use community data similar to the one we use for the compositional. So basically your species abundance change over time. You use this model to assess what is the interaction between them that is generating the changes that you might observe. And we have a vignette in the estar package where we show how it can be done. And we talk about the choices, and Viktoriia is actually going to go into a bit more details in the mathematics and the choices of how to do it. But I can already show you here, that for the Jacobian stability, the first thing we have to do is to get our data and make a series of choices on Mars about what we think is happening in our system. Viktoriia will go through them. And once you have them, it's quite, as you can see here, so you have several iterations of the model for it to stabilize in an estimation. And it's quite demanding for computationally, depending on the size. So I'm not going to run this here. But once you have this estimation, this is all the outputs of the model, you actually, we have a function called extract B, where you give the output of this model, and it's going to extract your B. Because if you see here, the model has quite some information it outputs, but this function makes it a little bit easier. You still have the job to go through Mars and understand it, but this function will get it in the format you need to give to the functions. And as I said, the functions, they really, they only need that input of the matrix, right? So let's go through them a little bit in detail, explaining what they are, and then at the end we look at our results for our data. So reactivity is this instantaneous rate at which the disturbance grows. So the perturbation grows at the moment of the disturbance. So as I said, this is really a schematic illustration. So I illustrated it as it's happening in the disturbance at the first time after disturbance, but you can imagine that this is like really instantaneous. So it's how that perturbation affects the initial response of your system to the perturbation. And if the value is bigger than 0, it means your system is initially destabilized. Here we illustrated like an undercompensation, but it could also go up. And if it's smaller than 0, then it didn't really react. It's relatively more stable system, you could say, initially at least. Then you have the maximum amplification. So it's how much the amplification, the perturbation is so amplified inside the system, so how strong the response is to that. And if it's close to 1, the system is stable, because you can think that this curve stayed more or less where it was, so it didn't change much. But if it's bigger than 1, again, it really departed from its original level here, and it could be either up or down. It means the system is not that stable. Then we have the initial resilience, which is the initial rate of return to equilibrium. Again, here we illustrate with a very clear point of return, but you have to think of it in terms of interaction strength, where this might not be as visible as here. And the larger its value, the more stable the system, because you can think that it's going back to its previous state faster, right? Then we have the asymptotic resistance, with in a similar fashion is the long-term rate of return. And again, the larger it is, the more stable the system, because it's going back to an equilibrium. And finally, we have stochastic invariability, which is the maximal response in response to white noise, so environmental noise. And again, this idea of invariability. So the higher its value, the more stable the system, because it's not varying much, right? And again, if we look at them for our study case here, we see some things that make sense for us. So the under higher concentration, we see a bigger reactivity. So this drop, I'm imagining it's the reservoirs pulling the response of the system down higher. But also similarly for the maximum amplification, where you see this drop affecting the whole system more. Whereas the return to equilibrium, it seems like our under lower is faster, that they return is more stable, because they stay kind of where they were, right? And finally, the variability is slightly higher for our system under higher concentrations of the insecticide. Again, that idea that we are thinking that it has to do that they were not great before. So even though it seems like they're varying more, they might not be, when I think in terms of how the community is actually changing through their interactions. And again, just to reiterate, the idea here is to show you how there are all these metrics that you can play around for a system, and how they can access different information, how this information might be or might not be, seem to contradict each other. This is for the user to decide when they analyze their results and they know their system. Here we tried just to be very encompassing of, okay, what are all the tools that we can bring together in this package. So my part is done. Viktoriia is going to continue with a little bit of detail in the mathematics behind estimating the B matrix.
Thank you, Ludmilla. And yeah, I will take over now with showing a bit behind the scenes for Mars, because if you were following, you probably have understood that in order to estimate this second group of Jacobian stability matrix, the key is actually to have this matrix B, the interaction matrix. And to infer matrix B, for now, the best tool that exists out there are multivariate autoregressive state space models, and they are implemented in Mars package. So these are so I will guide you a bit through, explain what it is and how to feed them in order to get that matrix B that we need to estimate the Jacobian stability matrix. So since it's a state space models, we have the hidden process, the true process according to which the system is developing, and we have the observation process that is the measurement of our system with a certain error. And when we talk about the true processes, basically we are studying the state of the system at time t as a function of the state of the system at time t minus 1. And we talk about system here in this particular case of Mars. It's the system is a community. So in our case, oops. I have to click on a different direction. Anyways, so on the left-hand side for our model for the hidden state process, we have a xt, which is a matrix of m of the dimension m by t that basically contains the unknown abundance values of m species. Our species are here in the row. I will quickly fetch the pointer. So we have our M species in the rows, and in columns we have time. So basically in rows like this, we have time series abundances for each species, starting with species 1 in the first row and through to species M on the M row. And in the last column, we have the abundances for those species for time t. So that's for our true hidden process that we cannot measure. And for the observation process, we have on the left-hand side YT, and this is a matrix of n observations of species or functional groups, because as we have seen in the example that Ludmilla has presented, we can also lump our species in several groups if it's biologically meaningful to our research question. And so we have those n observations in rows over t time points. So our columns are for the time points from 1 to t. And importantly, something does, okay. Very often in this kind of data, n is equal m. So we have as many observations as we have processes, but sometimes we may have replicates of our system. So we may have several replicates, and we can observe community in several different conditions. I will explain that a bit more later, and then n is more than m. Sometimes there is a lag. So now a bit more to explain you the structure of this model and what it actually represents. First, we focus on the state process. On the left-hand side, we have our matrix of m by t of hidden process abundances. And on the right-hand side, we have x t minus 1. So this is a vector of dimension m times 1 of abundances of m species at the time t minus 1. So this is the abundances one time prior to the t. And we multiply it with B. B is an interaction matrix, also known as Jacobian matrix in community ecology, and it basically shows the effect of the species of the abundance of the species in the column on the population growth rate of the species in the row. So beta 1m is the effect of the m abundance of the M species on the population growth rate of the species beta of the species 1. And on the diagonal, we have the effects of the population abundance of species on its own population growth rate. So that's what in population ecology we call density dependence. That's what we will have on the diagonal. Whereas on the off diagonals, we have this interaction strengths among our species. That's P. We want to estimate this. We don't have it. What we give as an input, what the user gives Mars as an input is x t minus 1 as an initial state, and sometimes also some other covariates I will show later. Now, U is a vector of intrinsic rates of increase for M species, which is often assumed to be 0 for a stationary process. So one main assumption of Mars is that the system follows the is at this quasi-stationary equilibrium, meaning that U can be assumed to be 0, but it's not necessary. In some cases, we can actually estimate U, and for those cases where we want to assume it's 0, which gives us more power to estimate values of the B, for example, and other parameters that we still have to estimate, then we can pre-transform a data in such a way that this assumption can be satisfied. So what is often done for that is demeaning the data or centering the data, where we remove the mean population abundance for each species from the time series. And sometimes even that scoring also is done. So on top of removing the mean, we also divide the value at each time point by the standard deviation of the whole time series. Important, something that I didn't mention at the beginning, is that our abundances, our input abundances, are usually log transformed prior to fitting the model, and therefore then U is the intrinsic rate of increase, because then we have x, the log of xt over xt minus 1 will be our intrinsic rate of increase. And then WT is a vector of process errors that reflects environmental stochasticity. It follows a multivariate normal distribution with the mean of 0 and standard deviation of Q, where Q is the matrix of variances and covariances that are between species due to environmental factors. So here we will have the covariances on the off diagonal that reflect the covariances induced by environmental factors acting on the species. Then for the observation process, we have our n observations in the rows over time in the column. So it's the matrix of the dimension n by t. And on the right-hand side, the first thing we have is Z, which is an association matrix that helps mapping the observation hidden process X on our, the true state process X on our observation process Y, so to our counts. And in the most cases, when n is equal m, then Z is just m by m identity matrix, as shown here. In other cases where n is not equal but more than m, I will show how to go about that, how to deal with that. Then A is the vector of biases that offset observations from their process values. And VT is a vector of observation errors that follow multivariate normal distribution with mean of 0 and standard deviation of R. Here, R is the matrix of variances and covariance matrix of observation errors. And as I said, this is just the basic formula, the basic structure. We may have more things that we can estimate and that we may want to estimate. So for example, for ecologists, we often are interested in the effects of environmental covariates on the population dynamics, and in this case, community dynamics, because I hope you already figured that we are working here with a community as a XT. So in this case, we can include the effect of environmental covariates as CT. CT is a vector of dimension p by 1 of environmental covariate values. Examples of such environment covariates are rain, food, and temperature, to name just 3. And these, the user supplies CT, the user supplies as the input to the model, to feed the model. And C, large C, is then the matrix that values of which we are estimating with the model. So this is the matrix of the dimension m by p, that consist of coefficients of the effects that our P covariates have on M species. So this first column will show of gammas will show the effect of our first covariate, say rain in this example, on each species in the row. So the first one is the effect of rain on the first species, on the abundance basically. The second would be on the second species, etc., through to M. And then we have in each column the effect of the next covariate on the abundance of each species in the row. And then P would be our last covariate. So in this simplified example, the effect of temperature on our species starting from 1 and through to M. So I hope that it's the meaning of WT is a bit more clear now. The WT are the residual process variances, covariances after accounting in the case of this model specification, after accounting for the effects of included environmental covariates. So it's the process variances, covariances due to other environmental factors that are not considered. That's basically environmental stochasticity. Similarly to how this is done with state process, we can also have covariates included on observation process. So we basically can have covariates that moderate or the covariates for our sampling effort. But I don't show this because we can't show everything in 1 hour. Now, I mentioned that it is sometimes possible to have data where we have multiple observations per process. So where N is more than M. Examples are, for example, several ditches in the case that in our case of insecticide applied to macroinvertebrate mesocosms that Ludmilla has presented, we had several ditches per concentration. So we basically have replicates per system. Or another example can be when we have spatial replicates of exactly same communities, say exactly same in terms of species richness or composition that are distributed in space. Another example can be that we can have one single system that is observed with different methods. So in Namibia, herbivore counts are conducted in one way as aerial survey and another way as ground-based survey. And we may want to combine the data coming from two different observation processes to reveal and better infer the underlying true hidden process of population abundances, how they change over time. How do we do this if we have more N, if N is more than M? Say, for a very simplified example, we have a community with 3 functional groups, and we have 2 replicates per community. Our Z contains, so our Z matrix that help us map X to Y contains M in columns and N in rows. So we would have 3 species because we have three columns, and then we would specify 2 ones because the first one here reflects one replicate that observes this species, and the second one maps then the second replicate that observes this species. And in analogous way, then we will have for the first replicate will be one for the second species, and this will be the second one for the second replicate. I hope I am making myself clear here. And it's important, so this will help us to specify correctly to let the model know how N maps to M. But also another thing that we have to think then about is about other assumptions of our model. So for example, how do we want to estimate our R? Remember our matrix R was the matrix of observation errors. And we can assume that they are all shared, that they're all the same across all 6 replicates in 3 different species. That would be the way to specify it. And in R speak, in Mars speak, you would say diagonal and equal, or we can assume, which may be more biologically reasonable, but costs more degrees of freedom, is that they are all unique for each species and replicate. So these are the things to consider. And now about things to consider, there are in fact many choices to be made when fitting this model. So I'll just highlight a few for you to be aware of. So in terms of matrix Q, our variance covariance matrix of process errors, one may want to estimate all values as being unique. So in this case, we will have on the diagonal the variances of 3 species to stick to a simplified case of 3 functional groups. And on off diagonals, we have the covariances between these species. So in this case, we would have to estimate 6 parameters. But we may also have reasons to assume that our species are independent of each other, in which case the off diagonal will be set to 0, and they all vary with the same variance, in which case we will estimate just 1 parameter, right, instead of 6. Or we may assume something in between, some other structures where, for example, the variances are different for each functional group, but they are still independent. So there is no environmental factors that force species to covary, or that they are covarying all with the same covariance Q, and they have 1 single variance. So in this case, we would need 3 parameters to be estimated, and in this case, 2. You see that depending on the choice, we make the number of parameters, and therefore also likely the precision with which we can estimate those parameters changes. Another example, when we consider our R matrix, so our variance covariance matrix of observation errors, we may have a system where we have the full knowledge of the system, where we are sure we have no error. For example, when we take plant releves and we estimate the abundance of each and single individual in our in our community, in that case, we can set R to 0 and assume that we have a full knowledge of the system. Another possibility is that we may have knowledge about the observation errors a priori, and that way we can specify, we can set the values in R to those a priori known values, and the model will not have to estimate them. For the B interaction matrix, usually we want to estimate all of them. So we usually set in Mars speak, we say B is equal unconstrained. However, of course, in ecology, there are cases where some species, interactions between some species are simply impossible. So if we a priori know that species 3 doesn't interact with species 2, never ever, it doesn't eat it, it doesn't compete with it, then we can set those interaction indices to 0, and that will make model easier to converge and to estimate other parameters. So the important message here is that we have to think carefully before specifying the model structure, and they have to put a lot of thought into how does our system function and what main processes we have to reflect in the model. And some more things to be aware of is that even though it is possible to specify the super complex model with many parameters, such model may not be identifiable. For the models that are identifiable, usually these are those for which the structures were already published, so you can rely on that and know that they're identifiable. Sometimes you can get convergence issues. They are possible, for example, but not only, when the model is degenerate. So it means that the elements on the diagonal of either Q or R matrices are going to 0, and then it will take forever for the model to settle on the maximum to achieve maximum likelihood estimation. So in that case, there are also some works around. Time series have been sufficiently long enough to estimate parameters, and of course, what's long enough depends on how complex your model structure is that you specify. There should be no missing data in your environmental covariance value, so in that vector CT. And the user must carefully specify the model. Usually the practice is specifying several alternative structures of the models, for example, with the different structures of our Q matrix or R matrix, because we believe that there are different representations of the nature. And then those models can be compared in terms of, for example, AIC to help us decide which model reflects the data best. And when in doubt, the best practice is to simulate a data using the process that you believe the system is following, and then fit Mars to that data to learn which model structures can still allow you to recover the parameters that you put into your simulation model and which cannot. And now I'm showing the slide that I'm showing since the 21st of February 2022. I'm showing this slide as a private person, not as a researcher. I'm showing this slide as a Ukrainian who was born and grew up in Ukraine. And I'm thankful to Ludmilla that she agreed and kindly agreed to me showing this. I'm thankful to all of you for standing with Ukraine and to your governments for supporting us, and you personally supporting people whom you probably knew fled from Ukraine or in any other way. We are deeply thankful for that. And please, I'm asking in these last days to not forget and do not give up on us. This last winter was very harsh. And yeah, we are still hoping, I think, instead of against the hopes. Thanks a lot. And I'll come back to research here.
Thank you, Viktoriia and Ludmilla. Tong.
Yes, I think we have a couple questions on the poll everywhere. Give me a second. Let me refresh the page. Okay, two questions. Is estar able to also perform pre-metric calculation smoothing of raw data, for example, in case of extremely noisy data set? Or would that step need to be performed by the user, and estar would be used for on the model results? So I think that's a question about pre-processing. Yeah.
Thanks for that question. So no, we do not pre-process the data. The estar does not provide such a functionality. I think there are quite a few packages out there or other tools for interpolating the data. And I think it also requires some knowledge of the system and assumptions as to how far you want to go with this interpolation. So we leave this up to the user to, if the data is really having so much holes and there are such large gaps, then I think it has to be in the hands of the user to determine how far you're willing to interpolate to fill those gaps before you can then give the time series that you obtained with whichever tools you used. Then you can supply to estar to calculate or estimate if it's Jacobian stability metrics.
Okay, thank you. And another question is about a very specific question. So for Jacobian initial versus asymptotic resilience, how is the temporal threshold? So differentiation between the two typically identified. I think that's with your slide, one of the questions.
Yeah, I think I'm not sure if because they're calculated in terms of the eigenvalues of that metric, right? So we don't really assess the exact time when it happens. I can actually show you the paper, the formulas that we use, because there it's not so much. So here, this is the initial one, and this is the asymptotic. So we don't like the initial is really the very first response, right? But we don't actually provide an estimation of when that happened, and the user doesn't really need to know it. It's really more about, okay, what is the instantaneous, what does the eigenvalues of our matrix tell us about the instantaneous return to equilibrium, and what is the long-term effect that we can expect. I hope this answered the questions. Do you have, maybe could you clarify something, Viktoriia?
I think that's good. Thanks. Yeah.
Okay, thank you. Next question. Can estar handle multiple year time series with intra-annual, so which is seasonal variability, where we would expect the state to return to a level that is different from the pre-treatment baseline?
So generally, the time step that you define is up to the user. So here in the example, that it doesn't have to be, first of all, it doesn't have to be regular. It's better if it's regular. You better not have those large holes and having very noisy data sets that in the other question someone was asking about. but the time step doesn't have to be a year. So it doesn't have to be only annual, say, counts. You can have a time step a month or a week, and then, well, of course, then it can deal with that seasonal variability. I think the question is here more whether the estar can disentangle what is the background natural seasonal variability versus what is the effect of the disturbance. If that's, I'm not sure if that's the question, then I think effectively by having the baseline or what we call reference system and then standardizing as we have these two ways that Ludmilla has presented to account for the baseline, either by using a log response ratio, so by log response ratio of your disturbed system versus undisturbed system that still follows some kind of seasonal dynamics. So either by doing that log response ratio or by taking the distance, I think log response ratio would be better here, I would say. You can effectively account for that seasonal intra-annual variability, but I'm not sure if that's like if the disentangling the effect of seasonal variation versus disturbance itself was the question. So I hope, I don't know if there is some way to get the feedback or to know if that's okay.
Okay, thank you. I think that should answer the question. Next one. What if the Jacobian matrix is time dependent? That is, so the audience is asking if he or she can estimate the matrix for each time step of the community time series. Does estar has a function that estimates the stability properties by time given the n matrix as input?
Yeah, so that's I think nothing is stable. We often in models, or we started in ecology from the rather simplifying assumptions where many things are assumed to be constant, but in fact, interactions, we are not only competitor and that's it. Our strength of interaction, even for competitors, changes over time. So if you have, to answer this question, if you have several Jacobian matrices over time, you can write a simple wrapper around the all the 5 functions that we have, like reactivity, maximal amplification, etc. So for all our Jacobian functions to basically apply them to your n Jacobian matrices, just to apply it n times. Yeah, we don't have a wrapper, but I think it's fairly, easy to do.
Sorry, I muted myself. I don't think there's any additional questions. Is there any questions in the Zoom chat, Judy?
Nope, none that came in.
Okay. Okay, we just answered all the questions. Thank you again, Viktoriia and Ludmilla, for giving such a great seminar.